Hi y'all, welcome back to another videocast presented by me, Mrs. Gabriel. This presentation will cover basic review of properties of Earth's atmosphere, types of pollution, and ways to prevent or minimize emissions into the air. So let's look at the picture here. In this opening case study, we're going to talk about Chattanooga, Tennessee. Remember, there are an infinite amount of case studies related to environmental science, and the ones covered in the text are common case scenarios. We're looking at an aerial view here, Chattanooga, with Lookout Mountain visible in the background. So after the Civil War, Chattanooga quickly developed lots of industry. This is one ingredient for air pollution problems. Another ingredient that makes human health at risk is the fact that Chattanooga is in a valley, which is like a bowl surrounded by mountains. This bowl traps pollutants, leading to high rates of respiratory disease. It was so bad in the 60s, before the Clean Air Act stepped in, that this photo would have looked very different. You wouldn't have been able to see Lookout Mountain. Strategies that cleaned up the air included controlling sulfur emissions, capping sulfur content of fuel, placing regulations on odors and dust, and making pollution monitoring techniques part of legislation. We'll learn about all the chemistry details of what occurred in this place and can occur all over. We'll also learn about what worked for them to clean up their air so that we can support similar strategies everywhere. Okay, so I took this screenshot on February 17th, 2015, which was a very cold winter day. Schools were closed, it was so cold. And the purpose of showing you this is to emphasize our progress in demanding clean air. 1. The EPA's Clean Air Act set an index of air quality standards to protect human health. This government agency is monitoring your air to inform you of the daily index. You have a right to know, legally. 2. It was a cold day and our air was dirty. It had a moderate level of pollution. On this particular day, it was because of particulate matter, which is a type of pollutant. So it looked all white and snowy and clear outside, but those particulates were there. They were out there, and you were breathing them in. Imagine a warm and sunny day. 3. This is not the only pollutant monitored. Look at the paragraph. They're also monitoring ozone, carbon monoxide, sulfur dioxide, and nitrogen dioxide. You'll learn why soon. For your information, these are 5 of the major 6 criterion air pollutants that the Environmental Protection Agency, under the Clean Air Act legislation, must specify allowable concentrations for. The 6th one, which is not shown in the AQI index, it's not shown. The 6th one is lead. Now, let's refresh our memory and understanding of the atmosphere. It mostly consists of inert nitrogen gas, 78%. About 21% is oxygen. Small amounts of other gases make up the rest of the atmosphere. The ones we need to pay attention to are listed in the variable gas boxes. Water vapor is very important in the transformation of primary to secondary pollutants. Carbon dioxide, methane, nitrous oxide, and ozone come from natural sources, but are increasing due to anthropogenic activities. CFCs are entirely anthropogenic, and they're really damaging if they make it to the stratosphere. So what is the stratosphere? You must know where it is, and you must know its significance to ecological systems and human health. If you understand the red line on this graph, you will understand the atmosphere more. From the bottom, follow me, from the bottom, in the troposphere, it gets colder and colder as we rise in altitude. If air rises and cools, clouds form. This is why most clouds are in the troposphere. Then, the temperature starts increasing. Follow the red line. This is the beginning of the stratosphere. Weather clouds do not form here. Airplanes are usually flying in the lower stratosphere. The stratosphere contains ozone. Look at the blue section of the figure. Ozone protects us from some damaging radiation. And notice where the blue is latitude-wise. More to come soon. You also need to remember how the sun's energy impacts the atmosphere. Read and remember the second bullet here. To clarify, look at the figure. Notice how the sun's rays are more concentrated at the equator. That means higher radiation. You also need to remember that the sun's solar energy creates our seasons because of the tilt of the Earth at 23.5 degrees and because its revolution around the sun. For example, if you look at the North Pole and all the way to the right, it is not receiving any solar radiation. This is our winter. We receive less radiation too. If you look at the North Pole in the summer, the way the Earth's tilted toward the sun, they receive 24 hours of daylight, although the radiation is not as concentrated, so you won't get as hot. Remember that the sun's radiation heats the earth and the air. If air is heated, it rises around cooler air, and eventually rising and moist air will form clouds. As it keeps rising, it cools. Cool air then descends. Sinking cool air does not form clouds, but this rising and sinking air circulates the atmosphere. This is called convection. This influences weather and climate big time. Since air has no boundaries or glass walls, it is constantly moving and ever flowing. So it is a global problem. The polluted emissions from one location can greatly impact the air in another location very far away. Pollutants are labeled as such if they harm plants, animals, human structures, or alter ecosystems. These are the big air pollutants. The starred pollutants are monitored by legislation under the Clean Air Act. You must know these by heart, know their names, know their sources, and know their chemical symbols. Also, get to know their effects on human health and organisms. This chart's in your book. This is a great study guide. If you can become more familiar with each pollutant and its corresponding information, you will be able to understand and articulate environmental science concepts with much more confidence and persuasion. For example, let's follow our enemy, sulfur dioxides. Recognize that the symbol for one sulfur dioxide molecule is one sulfur atom connected to two oxygen atoms. Remember that so that you can understand how chemical transformations occur with this pollutant. If you continue to follow the row, you can see that sulfur dioxides are respiratory irritants, they exacerbate asthma, and they harm plant tissue. It converts to sulfuric acid in the atmosphere, harming aquatic life and vegetation. So, where does sulfur dioxide come from? You need to know these sources. Fuels containing sulfur, including coal, oil, and gasoline. Coal-burning industries are the worst with sulfur emissions. Whoa, look here, and you can see how VOCs cause ozone formation. VOCs, volatile organic compounds. Then follow ozone, because VOCs cause ozone formation, so follow your ozone. And notice it causes other human health and ecological problems. So remember, ozone in the troposphere is bad. We don't like it in the troposphere because of what it does to us. Ozone on the stratosphere is good. We'll learn why. All right, particulate matter ranges in size from 0.01 micrometer to 100 micrometers. Particulate matter larger than 10 micrometers is usually filtered out by the nose and throat and is not regulated by the EPA because our nose and throat take care of it. Particles that are smaller than 10 micrometers are called particulate matter 10, and they're written as PM10. And they're of concern to air pollution scientists because they're not filtered out by the nose and throat, and they can be deposited deep within the respiratory tract. Particles of 2.5 micrometers and smaller, called PM2.5, are an even greater health concern because they deposit deeply within the respiratory tract, and they tend to be composed of more toxic substances than particles in larger size ranges. So know your primary pollutants, know your secondary pollutants, know where particulate matter falls. A little more about particulate matter. These are pictures to help you visualize how small particulate matter is. Particulate matter larger than 10 micrometers is filtered by the nose and throat and is not regulated by the EPA, remember. Particles smaller than 10 micrometers are called PM10, and they can be deposited way deep in your respiratory tracts. And if you just look at the sample on the right, it shows you sizes that you can compare, so you can understand this PM10 and PM2.5. And just for fun, here's some more pictures of particulate matter taken with an electron microscope. Okay, what we're looking at here is a city in China. It's a hot, sunny day where this picture was taken. It's a hot and sunny day where this picture was taken. People were wearing masks to filter smog. They come home with all white clothing, a tint of brown now. And this is bad stuff. China also has had so much industry that a similar scenario existed in a densely populated city for gray smog. So much sulfate is emitted that gray smog forms. As a matter of fact, Asian countries and their industrial gray sulfate smogs have been responsible for acidic rainfall on the west coast of the United States. And that's because weather and air masses travel from China across the Pacific Ocean to the western United States. It's not as bad now. China's been converting to natural gas and hydroelectric sources more and more. It's also reduced now because of massive tree plantings, because trees will filter the air. Well, doesn't this look pretty? Not. This is car exhaust under an electron microscope reverse image. Know this, and if you have time to look up the animation on respiratory impacts of various pollutants, please, please do. It's very informative. Just look up the keywords. Okay, so this is big. You should have paused and practiced your chemical symbols. You should know that SO2 is sulfur dioxide and that VOCs are volatile organic compounds. You should study this figure as well by looking at the sources, by following the black arrows to the primary pollutants. Then follow the blue arrow. When the primary pollutants get emitted into the atmosphere, they can also combine with water vapor and sunlight, and sometimes other oxidants, forming very damaging secondary pollutants. Remember, water vapor and sunlight, that UV radiation, help with the catalyst for this. A couple other things. Did you know what a VOC is besides what it stands for? Many VOCs include glues and gases. These compounds, when they're not burned, they emit vapors. So volatile organic compounds, which are VOCs, are a large group of carbon-based chemicals that easily evaporate at room temperature. And while most people can smell high levels of some VOCs, other VOCs have no odor. Odor does not indicate the level of risk from inhalation of this group of chemicals. There are thousands of different VOCs produced and used in our daily lives. Some other common examples include paints, cleansers, gasoline, benzene, nail polish and nail polish removers, mattress flame retardants, and carpet glues. They're all harmful to human health. Know the definition and examples of secondary pollutants. Also, if you want to understand how ozone forms and gets destroyed in the atmosphere, look it up online here. As I said before, many pollutants are formed naturally from fires, volcanoes, lightning, and plants. For example, shown in picture A to the left, a forest fire in Ojai, California produces air pollution. And B, to the right, the Great Smoky Mountains, they were named for their natural air pollutants that reduce visibility and give the landscape a smoky appearance. So I'll kind of explain that more. Long before anthropogenic pollution was common, the natural VOCs from plants gave rise to smog and photochemical oxidant pollution, hence the names of the forested mountain ranges in the southeastern U.S., the Blue Ridge and the Smoky Mountains. Large non-industrial areas such as agricultural fields can give rise to particulate matter when they're plowed, as happened in the Dust Bowl in the 1930s. So the IPCC, which is the Intergovernmental Panel on Climate Change, estimates that across the globe, sulfur dioxide emissions are 30% natural, nitrogen oxide emissions are 44% natural, and volatile organic compound emissions are 89% natural. However, in certain regions, such as North America, the anthropogenic contribution is much greater, perhaps as much as 95% for nitrogen oxides and sulfur dioxide. We, the humans, contribute significant pollutants to the air. Recent EPA data shows that on-road vehicles categorized as transportation are the largest sources of carbon monoxide and nitrogen oxides. The majority source of anthropogenic sulfur dioxide is the generation of electricity, primarily from coal. Among the sources of particulate matter are road dust, industrial processes, electricity generation, and natural and human-made fires. Notice the number one emitter of carbon monoxide and nitrogen oxides is on-road vehicles. That's your top two graphs. Also know the others. You need to know everything else on the list so that you can identify which emitters belong to which pollutant. For example, road dust does not emit carbon monoxide and nitrogen oxides. You should be able to recognize that that doesn't belong. Road dust does not belong to those pollutants. It's the number one emitter, however, for particulate matter. You should already know that from all the stuff and crap that you see on the snow when it's plowed. Are you paying attention? Do you know this stuff? Okay, criteria and other air pollution trends. Trends in the criteria air pollutants in the United States between 1990 and 2008 are shown here. All criteria air pollutants have decreased during this time period that we're looking at. The decrease for lead is the greatest. But the ozone in lead still exceeds standards. Only ozone and particulate matter concentrations exceed NAAQS, the National Ambient Air Quality Standards, on a regular basis. The cases where particulate matter exceeds national standards are not evident. It's critical to understand the harmful effects of tropospheric ozone. Remember, ozone is useful in the stratosphere. So here it is in the troposphere. Tropospheric ozone and photochemical smog formation are imperative for you to understand and be able to describe. Now look at both scenarios. With nitrogen dioxide sources, we're going to start with A. Look at A. In the absence of VOCs, there's no VOCs present in this scenario, ozone will form during the daylight hours and break down after sunset. Thankfully, it breaks down. But look at B. In the presence of VOCs, ozone will form during the daylight hours. The VOCs combine with nitrogen oxides to form photochemical oxidants, which reduce the amount of ozone that will break down later and contribute to prolonged periods of photochemical smog. This is because the nitrogen oxide is not available to break down ozone by recombining with it, and a larger amount of ozone accumulates. Smog is smoke and fog. Fog is water vapor. Smoke is emissions. Smoke and fog is smog. There are two types of smog, industrial and photochemical. Let's study the figure to understand the similarities and differences. So starting with industry, coal and oil combustion is putting emissions into the air. What are those emissions? Sulfur and carbon. Those emittents immediately react with oxygen in the atmosphere, forming sulfur dioxide and carbon monoxide and dioxide. Sulfur dioxide gas can further combine with H2O, forming sulfuric acid, which is H2SO4. This is not good stuff. Industrial emissions containing sulfur create gray smog. Cars, on the other hand, form brown smog. Let's look at how a car like an N for Nissan, N for nitrogen oxides, does this. They form photochemical or brown smog. Brown has an N in it too. Atmospheric brown cloud is a relatively new descriptive term that has been given to the combination of particulate matter and ozone. Derived primarily from combustion of fossil fuels and burning biomass, atmospheric brown clouds have been observed in cities and throughout entire regions, especially in Asia. The brownish tint that categorizes these clouds of pollution is typically caused by the presence of black or brown light-absorbing carbon particles and/or nitrogen dioxide. So this is what smog and haze looks like from pollutants. It's not pretty, and it's not safe. Just pay attention to Los Angeles in the early morning before all the emissions go into the air, and this is typical for Los Angeles in the afternoon. One more thing, the EPA says that half of the U.S. is breathing excessive levels of smog. Photochemical smog and ozone present especially difficult challenges to control, and the reason lies in the chemistry of smog formation. Are you paying attention? Make sure you regularly test yourself on this stuff. All right, again, back to primary and secondary air pollutants. The transformation from primary to secondary pollutant requires a number of factors, including sunlight, water from the clouds, and the appropriate temperatures. Conversion to secondary pollutants is more common during the day and when it's wetter or more humid. Temperature is a factor linked to air pollution conditions, as I just said, and here you're really going to see how it plays a role. If you look at the temperature lines for picture A, follow the blue line, you'll see an example of normal conditions. Whereas air rises, it cools. When the conditions are like picture B, a layer of warm air sits on top of the cooler air, and it traps emissions that accumulate beneath it. The trapped emissions cause a severe pollution event. This is common in valleys and in cities where high concentrations of vehicle exhaust and industrial emissions are easily trapped. And it also can happen in the winter and summer. So this is what we call, in B, a thermal inversion. But really, the problem is not the temperature as much as the fact that it's trapping the pollutants. Thermal inversion. Okay, now we're going to spend a little time on ozone. This is the big picture. Get it? Big picture. It shows how important ozone is in the stratosphere. To the left, we see that normal amounts of ozone, or O3, in the stratosphere protect the troposphere and its humans from bad ultraviolet radiation. To the right, we see how ozone reacts with CFCs in the stratosphere, meaning we have less of it. Therefore, we're not protected from the UV rays. Just pay attention to, in the stratosphere, what the molecules are doing as ozone gets broken up by ultraviolet radiation. So you should pause here, read, and take it all in, or maybe replay this part several times so you really can explain this yourself. Understand the figure and be able to write the chemical equations, and you're on the way to ozone greatness. Notice that the catalyst in these reactions is sunlight. Ultraviolet radiation. Some little things you should know about UV radiation. Ultraviolet radiation, the spectrum, is made up of 3 energetic ranges, UVA, UVB, and UVC, and they have different properties. UVA passes through the atmosphere without being absorbed and contributes to and possibly initiates skin cancer. UVB and UVC have enough energy to cause damage to tissue and DNA of living organisms. However, a protective layer of oxygen and ozone in the stratosphere absorbs over 99% of all incoming UVB and UVC radiation, which allows life to exist on Earth as it does. So we don't like the UVB and UVC, and the ozone in the stratosphere protects us from it, unless that ozone isn't there anymore. When CFCs are released into the troposphere, they make their way to the stratosphere, find where that happens in this figure. CFCs released in the troposphere, making their way to the stratosphere. The ultraviolet radiation has enough energy to break the bond connecting chlorine to the CFC molecule. Follow the arrows where you now see one chlorine atom zapped away from its CFC molecule. It immediately finds an ozone molecule and takes an oxygen. As you already know, we have plenty of diatomic and monoatomic oxygens floating around. A single oxygen then pulls an oxygen away from the chlorine monoxide, leaving a single chlorine to find yet another victim ozone molecule and do the same damage again and again and again. All right, please look at the chemistry I just explained. Visualize each step as it would be written out chemically. So, CFCs are bad. They're a class of anthropogenic compounds that are organic, whose properties make them ideal for use in refrigeration and air conditioning as propellants and aerosols. They're very stable, they're inert, they're non-toxic, this is CFCs, and they're even non-flammable in the troposphere. They don't degrade, they don't dissolve in water, and they don't undergo any big-time chemical changes. They just circulate in the atmosphere. But in the stratosphere, the UV radiation present is energetic enough to break the bond connecting chlorine to the CFC molecule. That's where all the trouble begins. Know the formulas, be able to describe them as well. Ozone concentrations are measured in Dobson units. Scientists have been measuring ozone in the stratosphere since the 70s. We are generally decreasing the trend. If we looked at ozone over the poles, we have a much thinner layer in the stratosphere. The ozone hole is not technically a hole where no ozone is present, but is actually a region of exceptionally depleted ozone in the stratosphere over the Antarctic that happens at the beginning of the southern hemisphere spring, which is August to October. Under normal atmospheric conditions, the two chemicals that store most atmospheric chlorine, hydrochloric acid and chlorine nitrate, are stable, but in the long months of polar darkness over Antarctica in winter, atmospheric conditions are unusual. An endlessly circling whirlpool of stratospheric winds, called the polar vortex, isolates the air in the center. Because it is completely dark, the air in the vortex gets so cold that clouds form, even though the Antarctic air is extremely thin and dry. Chemical reactions take place that could not take place anywhere else in the atmosphere. These unusual reactions can occur only on the surface of polar stratospheric cloud particles, which may be water, ice, or nitric acid depending on the temperature. When sunlight returns to the South Pole in October, UV light rapidly breaks the bond between the chlorine atoms, releasing free chlorine into the stratosphere, where it takes part in reactions that destroy ozone molecules while regenerating the chlorine, known as a catalytic reaction. A catalytic reaction allows a single chlorine atom to destroy thousands of ozone molecules. And I think you get the picture from there. Ozone is not our enemy in the stratosphere because we don't live up there, and its ability to absorb UV radiation and shield the surface below makes stratospheric ozone critically important to life on Earth. This shows one way ozone harms life on Earth in the troposphere. That's because we, and plants and animals, live in the troposphere. So it decreases crop yields when it's dense in the troposphere. Efforts to reduce ozone depletion have been working, as you saw in the previous chart. The most famous effort has been by the Montreal Protocol Treaty. CFCs are persistent. They last for tens to hundreds of years. This is a long-range solution that we're already beginning to see results with. If we all stick to the treaty, scientists hope by the year 2100, skin cancer rates should start to finally decrease. Air pollution affects ecosystems like forests, especially acid precipitation. Some examples are shown. And these are examples of air pollutants and their effect on forests, and specifically we're now looking at acid rain. Acid deposition occurs when nitrogen oxides and sulfur oxides are released into the atmosphere and combine with atmospheric oxygen and water. These form the secondary pollutants, nitric acid and sulfuric acid. These secondary pollutants further break down into nitrate and sulfate, which causes the acid in acid deposition. This is going to start looking redundant, but now we're discussing specifically acid deposition. It originates from sulfur and nitrogen oxides, SOXs and NOXs. They react with water to form sulfuric and nitric acids. Know the symbols for these chemicals. Acid deposition doesn't just harm our precious forests. It also lowers pH, leaches metals found in soils, releasing them to the surface and groundwater, and damages human structures. According to the EPA, normal clean rain has a pH value of between 5 and 5.5. Remember that 7 is neutral. So 5 to 5.5 is slightly acidic. However, when rain combines with sulfur dioxide or nitrogen oxides produced from power plants and automobiles, the rain becomes even more acidic. Typical acid rain has a pH value of 4. We call it acid rain officially when the pH value is under 5.5 or lower than 5.5. So what are the effects of acid rain? Notice where we live, that we are more likely to experience the effects. Predict some effects before you look at the next few slides. The effects of acid rain, anthropogenic acid rain, are astounding. Know the many effects. Thankfully, the Clean Air Act and its many amendments that were passed in the 1990s have reduced the acid deposition causing all this damage. The greatest and most disturbing negative environmental effect of acid deposition has been on aquatic ecosystems. Lowering the pH of lakes and streams has caused decreased species diversity and impacted reproductive abilities of these organisms. Most aquatic species, especially salamanders, don't survive in a pH below 5. Leaching of metals such as aluminum and mercury can impair the functioning of aquatic organisms and kill them. These metals also bioaccumulate and biomagnify through trophic levels, harming even the humans that eat them. And the red spruce has been harmed to a point of forest destruction. Human structures are also weathered quickly from acid deposition, including famous Greek monuments. They are eroding away by the day to our damaging acidic pollutants. These acids react with building materials, specifically limestone and marble. The calcium carbonate reacts with the hydrogen ions. Acid deposition in dry form also erodes exposed painted surfaces, including car paint. It's officially called acid rain at 5.5 or lower. Also, remember the pH scale. 7 is neutral. Acid deposition has been reduced in the U.S. as a result of lower sulfur dioxide and nitrogen oxide emissions. This is a result of the Clean Air Act amendments passed in the 90s. Even though the use of cleaner fuels with less impurities has helped, these technologies and innovations have helped reduce emissions even more after combustion. A fluidized bed combustion chamber in which granulated coal is burned in close proximity to calcium carbonate reduces sulfur dioxide emissions. The calcium carbonate absorbs the sulfur dioxide. It leaves behind a product called gypsum, actually used in wallboard, known as sheetrock for houses. A catalytic converter is a device that uses a catalyst to convert 3 harmful compounds in car exhaust into harmless compounds. The 3 harmful compounds are hydrocarbons, which is in the form of unburned gasoline, carbon monoxide, formed by the combustion of gasoline, and nitrogen oxides, created when the heat in the engine forces nitrogen in the air to combine with oxygen. Remember that carbon monoxide is a poison for any air-breathing animal. Nitrogen oxides lead to smog and acid rain, and hydrocarbons produce smog. In a catalytic converter, the catalyst in the form of platinum or palladium is coated into a ceramic honeycomb or ceramic beads that are housed in a muffler-like package attached to the exhaust pipe. The catalyst helps to convert carbon monoxide into carbon dioxide. It converts the hydrocarbons into carbon dioxide and water. It also converts the nitrogen oxides back into nitrogen and oxygen. I think this picture speaks for itself with a baghouse filter. This is a device that captures particles removed by a series of filter bags. This guy, the electrostatic precipitator, gives negative charges to particles, then collects them on a positively charged plate, because opposite charges attract. Then they're collected for disposal, usually at a landfill. The scrubber uses water droplets to attach to particles, dropping them into a bottom unit. The collection of sludge is then disposed of in a landfill, just like all the other particles collected. Then we have all these particles are collected, all of them from everything I just showed, go to the landfill. The one downfall of all these technologies is that we slow the airflow down, and therefore we have to use more energy at the industrial site. But they've made a tremendous difference in pollution emissions. Amendments to the Clean Air Act allowed free market programs. In the provision, it allowed the buying and selling of allowances that authorized the owner of a factory that emitted sulfur to release a certain quantity of sulfur. Each industry was allowed to emit 1 ton per year. They were given an allowance. The permits, or allowances, were awarded annually. Emitters were not allowed to emit more than a previous permit. Penalties were enforced if emissions went over. If they wanted to exceed previous emissions, they could buy permits or allowances in the open market. This is similar to a cap-and-trade market economy, as shown in this figure. Your emissions are capped. This is your maximum allowance. And if you can go with less, you can trade. Acid deposition has been reduced in the U.S. as a result of low sulfur dioxide and nitrogen oxide emissions. This is a result of the Clean Air Act amendments passed in 90 and 95. We've taken additional actions such as incentives like tax reduction for lowered emissions, penalizing for increased emissions, and incentives for using public transportation over driving cars. Indoor air pollutants are bigger killers than outdoor. They cause more deaths than outdoor pollutants and depend on culture, climate, and economic and socioeconomic situations. Developed countries are at higher risk. 3 billion people use wood, animal manure, or coal in their homes for cooking and heat. These biomasses and coal are usually burned in open pits. So these are less developed countries. Such as this woman in a home in Zimbabwe. Indoor air pollution in the developing world is a problem because combustion is incomplete. There's usually no exhaust system and little ventilation, leading to carbon monoxide poisoning and particulate matter toxicity. The World Health Organization, the WHO, estimates that 1.6 million deaths annually occur due to indoor air pollution in developing countries. Oh, and you're at risk also. Developed world issues are covered in this chart, but you need to also know the health effects of each pollutant here. For example, old paint contains lead. When lead dust is inhaled, or a toddler ingests lead chips of paint, it leads to lead poisoning, which causes organ damage and neurological impairment. Know the sources of your indoor pollutants and the health risks associated with them. The best way to reduce your exposure to them is to ventilate your home often by opening doors and windows and by stopping the purchase of the sources. How many of these pollutants that can harm your health are in your home right now? Look at the source column. I bet you have most of these items. Find Maryland on this map, and you will see that you are located in a moderate risk radon zone, which causes lung cancer. Talk to your parents about whether your home was ever tested. It would seep from the ground through the cracks in your basement. You can buy radon test kits in Home Depot if you want to check your home. Many newer buildings in developed countries like ours are so well insulated that they prevent air from leaking out. That's great for energy efficiency, but not so great is the toxic compounds that get to build up in the airtight space. The usual culprit causing this situation is called sick building syndrome. The symptoms may be any of the ones listed here. The EPA has identified the problems as related to ventilation, chemical contamination from glues, carpeting, furniture, cleaning agents, and copy machines, nearby vehicle exhaust, and molds. So, that's the end of your education on air pollutants. I hope this has opened your eyes to the problems and solutions. I hope you are part of the solution. Until next time, breathe in, breathe out, breathe clean. This is Mrs. Gabriel, out. Well, this is the end of part 1 on air pollution. Please make sure you study and review it a few more times and then move on to part 2. Well, this is the end of part 1 on air pollution. Please make sure you study and review it a few more times and then move on to part 2.